Okay, now that we know the basics of series circuits, let's take a look at some actual examples of full series circuits and see all the different things that we can find. We have a very basic series circuit here with two resistors in it and a battery. The battery has a voltage gain of 6 volts. The first resistor has a resistance of 80 ohms. Second resistor has a resistance of 90 ohms. We are looking for Req, the current in the circuit, voltage drop for each resistor, the total voltage drop of the circuit, and we're going to learn how to draw in ammeters and voltmeters in a circuit diagram. This might seem overwhelming to you. I like to treat these as if they were Sudoku puzzles. A Sudoku puzzle, when you put the numbers in the grid, is very overwhelming if you look at the whole thing, but if you concentrate on just what you know that you can do right off the bat, you eventually find that you can fill in the entire grid. It's the same thing for solving these circuit questions. Let's start off with something easy, Req. We know that the equivalent resistance for a series circuit is given by this. R1 plus R2 is equal to Req. R1, we're told, is 80 ohms. R2 is 90 ohms. So Req must be the sum of those numbers. 80 plus 90 is 170 ohms. Good. That one's all set. Now, remember, Ohm's law applies not only to individual pieces or components of the circuit, it also applies to the circuit as a whole. I can use Ohm's law to find the current in the entire circuit, even though I don't know the voltage drops here, but I do know the voltage gain for the entire circuit. It's 6 volts. So I can do this. Vt equals I Req. I know the total voltage drop of the circuit. I know it's 6 volts. Or the voltage gain, I should say, is 6 volts. I also know the equivalent resistance because I just found it. 6 volts equals I times 170 ohms. I divide both sides by 170. 6 divided by 170 is, with some rounding, 0.035, and that's units of amps. That's the current in the circuit. And remember, the current in a series circuit is the same everywhere. So that applies not only here, and here, and here, but here, and here, and here, and here, and here, and everywhere in the circuit. Now that I know the current through the two resistors, I can find the voltage drop for each of them. So here's for the 80 ohm resistor. We use Ohm's law, V equals IR. V is what we're looking for. I is 0.035 amps, multiplied by a resistance of 80 ohms. We get a voltage drop of 2.82 volts. And for the 90 ohm resistor, I can do similar. Remember, a current is how much charge is flowing past a certain point per second. A voltage is really telling us how much energy is given off by a certain circuit component divided by how much charge is passing through it. And the resistance is just the quotient or the ratio of those two, V divided by I. Remember those definitions as we're doing this. It shouldn't just be mindless calculations. All right, let's get the current back. Okay, there's the full current. Multiply that by 90. We get 3.18 volts. So we've got the voltage drop for each. Now notice we also need the total voltage drop of the circuit. Vt must equal V1 plus V2. Total voltage drop is therefore 2.82 volts plus 3.18 volts. 6. The total voltage drop is 6 volts. And we could have gotten that because we know that the total voltage drop in the circuit is equal to the voltage gain of the battery. Very straightforward. Now the two new things that we're going to look at is placing a voltmeter and an ammeter. Voltmeter where it can measure the voltage drop across the 90 ohm resistor. Ammeter to measure the current. Well, let's stick with ammeter first because that's really easy for this one. It does not matter where you put the ammeter because the current is the same everywhere. Here's how you draw in the ammeter. You draw a circle and you put an A on it. And I like to kind of look like we're hooking it in there. That is an ammeter. Now the voltmeter has to be drawn very specifically, and this is the one that people mess up. Remember, in the simulation, the voltmeter, you didn't just wire it into the circuit. You had the two little probes and you put them across or around the resistor. That might look something like this. See how it's just like these are the little probe arms here? Here's the voltmeter, here's the thing that's actually reading it, and they go across the resistor. If you were to do these reverse, if you were to put the V in like this, wired right into the circuit, or you put the A across the resistor, like this, That would be wrong. That would actually, in real life, possibly break either the voltmeter or the ammeter, especially the ammeter. You don't want to do that. There's a reason that you would end up doing that. I'm not going to get into it right now. I can talk about it in class a little bit, but that's a really easy way to fry the tools that we actually have in class, and these things are a little expensive, okay? They're not free. So we need to make sure we understand how to wire up a voltmeter and an ammeter. Let's go to the simulation just to check this. We have a 6-volt battery and an 80 ohm resistor and a 90 ohm resistor. And now we're going to check everything. We know the equivalent resistance is going to be 170 ohms. So what I'm going to do is I'm going to insert the ammeter right here just to prove that. Okay. We said that the current was going to be 0.035. We get a current of 0.04. Within rounding, that's absolutely fine. I'm going to break this off, and I'm going to connect this at some other point just to prove that the current is the same everywhere. And what do you know? It is. So that's the current. If we want the voltage drop, and notice how the ammeter is wired in. It's right in the circuit. The voltmeter is not going to do that. The voltmeter has these little probe arms, and they go around things. The probe for the 80 ohm resistor, or the voltage drop for the 80 ohm resistor, is 2.82 volts. For the 90 ohm resistor, 3.18. And the total voltage drop is 6 volts, just like the voltage from the battery. And notice again that I place a voltmeter with the probe arms going around the circuit component, not right wired right in. Okay. One other thing I want to show, sometimes people think that the order of the resistors matters. I'm going to show you that it doesn't. If I just change the order of these, if I make this the 90 ohm resistor, and I make this the 80 ohm resistor, notice that the total current is still the same. The voltage drops are still the same. 3.18, 6 for the total, and 2.82. They've just reversed. So the voltage drop doesn't go with the order of the resistors, it goes with the size of the resistor. Okay? Notice also that the bigger resistance has a bigger voltage drop. And that makes sense if you think about it in the context of Ohm's law. Okay? So that's a very basic series circuit problem that you might see. I'm not going to do a simulation for this one because the resistances are a little bit bigger, but we're going to calculate it anyways. Now we have a series circuit with 3 different resistors in it, R1, R2, and R3. We know it's a 12-volt battery. We know the resistance for R1 and R2, 1800 ohms, 2400 ohms, and we know the voltage drop for R1, which is 3 volts. We don't know anything about R3. We are going to find the current, the voltage drop for the other 2 resistors, the equivalent resistance of the circuit, the size of the resistance of R3, and we're going to once again place a voltmeter and an ammeter. Remember, it doesn't matter where we put the ammeter, so I'll just put it right here. Remember, we wired that right into the circuit. Place a voltmeter where it would go to measure the voltage gain of the battery. This will work as long as the probe arms are around the battery. That's a symbol for voltmeter. That's a symbol for ammeter. Now, how are we going to solve the rest of these? Well, a lot of these we can't quite get to yet. We can't find REQ because we just don't have enough information yet. We can't find V2, V3. What we can find at first is I. Now, how are we going to find the current? Remember that Ohm's law applies not only to the circuit as a whole, but also to each individual piece. If we know the voltage drop for resistor 1 and the resistance of resistor 1, then we should be able to find the current going through resistor 1. And since it's a series circuit, that current should be the same at all locations. So what we're going to do is we're going to do I'm just going to do for 1 equals the current at 1 times R1. That's 3 volts equals I1 times 1800 ohms. I1 is therefore 0.00167 amps. Get used to small currents. They're usually quite small. That's the current everywhere, okay? Not just through this resistor, but through every one of them. Now that we have the resistance, now that we have the current, I can figure out the voltage drop for R2. V2 equals I2 times R2. V2 is, let's see, that's what we're looking for. The current is 0.00167 amps. I'm just rounding there, obviously, but I'll use that. And let's see, 2400 ohms. The voltage drop for number 2 is 4 volts. Now, I can think of a couple different, well, right now, we could figure out, there are a couple different ways to do this. The order doesn't matter at this point. That's what you'll notice sometimes. Sometimes you have to start a certain way, but then the order that you solve things in kind of changes. I can find V3, actually I think I do have to find this one right now. I can find voltage drop 3, even though I don't know the resistance yet, because I know the sum of the voltage drops in the circuit must be equal to the voltage gain of the battery. So that's VT, total voltage drop, equals V1 plus V2 plus V3. That's the rule for series circuits. It's right in the reference tables. Total voltage drop must be 12 volts because that's the voltage gain of the battery, equals 3 volts for R1 plus 4 volts for R2 plus V3. V3, very basic math. Let's see, that's 7. Subtract 7 from 12. That gives you 5 volts. That's V3. Now, doesn't matter whether you do R3 or REQ next. You can do either or. REQ we could find right now by doing, let's see here. Oh, I had this wrong. VT equals I times REQ. Total voltage is 12 volts. The current is 0.00167 amps. We can find REQ from that. We get, with some round, let me do this. 12 divided by 0.001. There we go. That's about 7,200 ohms. We could have solved for R3 first by doing this, by saying V3 equals I3 times R3, 5 divided by 0.00167, and found that it was about 3,000 ohms. Or we could have done this. So let me just write that down quick. V3 equals I3 R3, 5 volts. And just as a check, we could have also found R3 by using the definition of equivalent resistance for a series circuit, adding all the resistances together. REQ was 7,200 ohms plus 1,800 ohms plus 2,400 ohms plus R3. 7,200 minus 1,800 minus 2,400 is 3,000. So it makes sense that that is what we get doing two different ways. That checks out. Okay. There's a very basic intro to series circuits. Next, we're going to talk about parallel circuits. They are a little bit more complex, and you do need to be able to tell the difference. That's the biggest thing. You need to be able to tell the difference between a series circuit and a parallel circuit, but otherwise, these are pretty straightforward. And I actually enjoy kind of doing this circuit analysis. It's kind of fun. It's almost like a game. And you can usually check most of your answers, maybe with a little bit of changing the numbers around with the simulation. Okay? I will talk to you guys later when we talk about parallel circuits. Bye.